esteemed attendees. Our journey through quantum computing applications takes a fascinating turn with our next speaker. Please welcome Oskar Mencer, CEO of Mencer Technologies, who will explore the deployment of QUBO on Groq and running quantum computer programs on a large-scale data flow computer.
Well, first of all, thank you for everybody who's stayed all the way to the last talk of the day. It was a very tough afternoon, starting with a research laboratory, an academic talk, and then all the way into the depths of mathematics. So I'm going to try to turn the tables and go all the way back to reality and what is practical today and what one can do today with technology that we actually have and can use. Of course, focusing on finance in this particular talk. Let me just try here. The technology, yes, this works. A little bit as a background, I started a company now some 20 years ago to build computers for people who have something that they would like to compute that they cannot compute today. So I would usually start with people and say, is there any other way that you could do what you want to do without talking to me or without worrying? If there is really absolutely no way, if they've tried everything else, then that's where I got excited and started to work with people to build special purpose computers for special problems that were too hard at the time. Of course, we didn't have quantum computers 20 years ago, and one might argue that we still don't have them, but it's a longer argument. And so more recently, my company joined a larger organization called Groq that makes special purpose chips for AI. And for this particular talk, I would like to describe what it is that we can do with this new technology, simulating quantum computers for financial applications. So that's something that we can do today. And we're starting off with an actual quantum computer. This is one of my proudest moments, standing here next to the actual quantum computer built right here, very close to where we are at TII. Of course, we cannot see inside, but I was told that there is a quantum computer inside of that white part here. It's just a tremendous accomplishment to be able to build these machines. And yet, we don't see these machines being used actively in industry too much yet. So we are still in the research phase. We do see from all of the talks that we've heard today and then what's coming tomorrow and afterwards, that the potential is immense. You could compute unbelievable things once these machines are going to be available for commercial use. So one of the things that I looked into here, I was getting close to the actual machine. See, how does the data go in and out of this thing? And of course, there's a classical computer right next to that, behind me there in the shelf. Very kind of standard equipment to get the data transformed into something that can go into the quantum computer and then back out again. And you have to imagine the quantum computer is there in the fridge at very cold temperatures. And so we have to get that data in all the way into the cold, and then we have to get the results back out again from the very cold down here at the bottom of the barrel, all the way back out into the real world. And that's where the problems are, or some of the problems are in quantum computing today. So what we've started looking at is how we can improve and address that problem of getting the data in and out of that quantum computer. And just to kind of give you a little bit of a sense for that, there are chips that are called FPGAs that are being used for that, where you can change the circuits around and you can adapt them to whatever is needed. And then people do that in order to transform the signals into something that can go into the quantum computer all the way into the cold and then back out again. And we are building these things out of standard components. And now with Groq, with a new technology from AI, we have the ability to enhance that kind of environment to help people to transform the data to go into the quantum computer, which is easy because on the way in, we don't care. But on the way out, of course, we have a huge problem of reading the correct result out. That's where people talk about noise and error corrections and issues, because there is no problem with computing until you actually want to see the result. And it was, I think a previous speaker mentioned that we would be computing something and we may or may not look what the result is. Because the looking at the result is the actual problem. The computing goes very, very fast on the quantum level. Measuring what that qubit has actually decided to do, that's a much, much bigger problem that becomes a physics experiment. So we can use computation and kind of signal processing to improve that. So that's how I kind of got into that whole environment. I started thinking about the issues beyond that. Given that there are going to be these very powerful machines, what can we do today to prepare ourselves for that? And obviously, we'll need to be writing a lot of software for these new machines because the software is going to be completely different. The math is going to be completely different, and then the software from that is going to be yet very different. So here, the idea is to use a whole new chip technology that we have that gives us the fastest possible way to compute today and simulate the quantum computers of tomorrow to be able to write software for it, to see what could be written, and to have something to run it on. So these are chips that are available today. You can get them, and you can simulate your quantum computer. And you, of course, want to do it as fast as possible. So with that, you have the opportunity to use the latest chip technology that has been developed for artificial intelligence, but can also be used for quantum computing. So that's kind of a comparison of what we are working with. This is what we call a static data flow machine used today for language processing. So this is the fastest way that you can run a language model today. You have things like ChatGPT or Llama or Mixtral, or JAIS here in the UAE, Falcon. You can run all of these models on that chip a lot faster than you can on kind of conventional, very messy, very complex GPUs here on the left. So that is slowly starting to be established. The reason why this works fast is because it's all pre-scheduled, it's all predetermined. You have about 1 million arithmetic units inside of a chip, very regularly laid out. You tell everyone what to do, you stream the data in, and the data comes out on the other side in a computed way. So that way you get the full power of all of the arithmetic in there. You have things like SRAM memory, so you have memories inside of that hold the data, that give you infinite access to that data inside of the chip. So it's essentially taking computer science and throwing it in the bin. Everything you've learned about Intel and processors and all of that nice stuff has to go. So clearly there's also quite a bit of conflicts that are arising from that approach. But at the end of the day, since it's so much faster, there's always a commercial opportunity to do things that nobody else can do. So we have this technology now, and how do we now use that to simulate a quantum computer? So as we've seen earlier today as well, there's a QUBO formulation. The QUBO formulation is a quadratic unconstrained binary optimization. So what does that do? It gives us a matrix, and we solve this matrix. A regular quantum computer also solves this matrix. So by having a solution of that matrix, you can essentially run any program that you would like to write for a quantum computer. So now, by being able to solve that or run that problem also on our machines, you get to run much larger problems. We've seen qubits, people talk about 400, 1,000 qubits. With these machines, you can run problems up to hundreds of thousands of variables. So you can be 10, 20, 30 years ahead of the quantum computing community, writing software that you can run today on machines that exist today and demonstrate what the problems are that could be solved, what can be done in the future with these machines that we're going to have. So this is how the formulation looks like. And then, of course, there is all the physics behind it. You have simulated bifurcation with the Ising model, and that QUBO formulation translates into an actual quantum computation. The QUBO instance is stored directly on the chip that I showed before, so there is no kind of memory and hierarchy and computer system as we are traditionally working with, but you have the chip with all of its memory and the arithmetic in one bit, and the bandwidth inside of that ends up being a lot higher. So because of that SRAM inside the memory that we have inside the chip, we also have this way to move data in and out much faster, which is of course the key problem in regular computers, and it's made a lot worse when you do quantum computing, where you have to get the data through some kind of thick metal cage of cooling that gets you down to the qubits. So here, this is a bit more detail. This is what gets the computer architect's heart pounding. I'm not expecting everybody here to be jumping up and down in excitement from this, but just to see that people in this field, that's what they like to look at, where the data is going, how it's moving around through that chip, and why this is actually a much more efficient structure to do computations. Happy to take this offline with whoever is excited about these things. Really, for this talk, it suffices to say there is this quantum formulation of a problem translated into a QUBO that optimization problem can be solved, and we can run it on the chip that is attached in your PC. So you get a PC, you plug the card in, and you can do computations. That is limited at the end of the day by something called a PCIe, which is the PCI Express thing. If you open your computer, you will see these slots, and you get these cards, and you stick them in there. That's the PCI Express slot that delays things, because you have to get in and out of the machine. So what we're doing is we're saying, okay, that's just nice for playing around, but for real problems, we take many of these chips, maybe up to a few hundred, and we make them work together. So we connect them all up, and we make hundreds of these chips operate as one. And by doing that, we can solve here up to 225,000 by 225,000 large matrices. So these are really, really large matrices. We're not talking 10 or 100 qubits here. This is super large, something where you could take, I don't know, the entire options table of an equities exchange and just look at the correlations of all of these things, or do computations on identifying something inside of that. A little bit more detail here on how these communicate. there is a special purpose proprietary protocol, cables that go between these things that allow us to make all of the chips operate as one big computing element. Maybe you could call that one processor, but that would be a processor that as large as like 10 racks. So going back to kind of the way that that Seymour Cray would have imagined building machines 30, 40 years ago, trying to put them together in a kind of circular shape sometimes, as they did before, to make the entire machine solve one problem, but solve that problem faster than anybody else. So that's where we are then with this technology, and say, okay, how fast is that? And we're looking here at the teraflops and how that increases. As you increase the machine, you put more and more nodes together, you see the size increases, but also the QUBO instance size. So the larger the machine is, the bigger problem you can fit in, then you solve all of that in one go. Now, there is the brute force computing part, which is, of course, what the quantum computer would also do, which is solving the actual optimization problem. But there is a equally important part, which is the driver. How do you go from your problem domain, what it is that you actually want to solve, into the QUBO? How do you go into the kind of optimization that you want to do? And so what we are working on for particular application domains is the driver side of things. How do you convert your financial variables into the actual QUBO variables of what it is that you're trying to optimize? And so for different application areas, this is each time an effort from scratch. Here is one example. This is the kind of driving example of quantum computing, integer factorization. We figured out that we can solve integer factorization with quantum computers and therefore break encryption. And this is how you would formulate this. But of course, it depends on what you're actually doing, right? Nobody's factoring integers. At least very few people sit at home and factor integers. But we do encryption. We have AES, or we have other encryption algorithms. We send messages over the internet, and we would like to maybe keep them secret. So then the algorithmic details of these enter into the game of breaking AES, breaking any other encryption algorithm. So there is a equal kind of counterpart to the quantum computing, to the QUBO part of it, which is the algorithmic side of what you're actually trying to do. Here's an example of how you map just the integer factorization over to a QUBO. Again, I'm not going to go into all the details of this. Getting to the actual quantum for quants, the actual applications, what can we do with this? So you have a simulator, you can simulate large problems. One of the things that we looked at, because of our background, we've been building machines for high-frequency trading. So we make a little box, and then our customer would take that box, put it into an exchange, and connect it with a cable. They would get a promise from the exchange that that cable is equal length to each one of the customers. And then they put some circuit there, and they say, well, you know, within 3 nanoseconds, I can get the market data, I can read the latest order book or whatever it is that the message that is coming in, make a decision, buy something or sell something. So that's the left side of this here. And we've been doing this for 10, 15 years. There is a very active community out there, and people are usually building these little boxes themselves. Very few go with vendors like us, but it's still nice to kind of participate in this. We've also been building the other side at the exchanges that then receives these things. So there's the two sides of the cables. There's this cable, and then you have the trading people who send the messages, then you have the guys who receive the messages and then go into a matching engine and match the transactions and do an actual transaction. So what we can do now with with the AI chip that we have here, we connect through the proprietary cable, and we could have a QUBO problem formulated in terms of which of the equities or whatever it is options to buy, as well as when to buy them, as well as how much. So it's like 3 decisions that you need to make, and you can formulate some of these things as optimization problems. Because the cable is proprietary and is pre-scheduled, you have ultra low latency. So you have the minimal latency into the optimizer and back out again. So then you can say, okay, but this is for very extreme people. I mean, how many people really need to be trading on the nanosecond level, and who cares about 10 nanoseconds, 20 nanoseconds? It's kind of specialist kind of people. They live in Chicago. It's cold in the winter. It's kind of a very strange place. So for the rest of us out in the real world, algorithmic trading, a little bit slower. You work on seconds, minutes. Some people even take days. Other people will take weeks to figure out what it is that they need to do. But even then, you still need to compute something to optimize whatever it is that you're doing. So you can formulate your optimization problem here, and we have two activities. Of course, with the QUBOs, you can formulate a quadratic optimization problem. You could look at various metrics that you are given for your trading. So you probably have given some kind of metrics that you need to optimize, and then you can formulate that as a QUBO and start using kind of the ideas that people are kind of pushing for quantum computations in finance that will be available 10 years from now, 20 years from now. You can run them today already. Okay, slower, right? It's not going to be as fast as the quantum computer, but it's better than nothing. And we can learn from that. And from learning from that, we can then be ready when these machines are there to actually know how to use them, what to use them for, how to gain some advantage from that. So that's the kind of general idea. I like to combine this usually with the XTX part up there, which is giving us some correlation engine, a way to kind of find connections between data, which we also can use for the error part of the quantum computing. So if you know what your results need to be, the correlation part can be used to reduce the noise and get better results. In this particular case, to feed information into a quadratic optimizer, it helps to start with what are the relationships between all of the different feeds of numbers that you have. So it's kind of a good package, and it naturally maps onto the technology that we have. So it's a kind of good starting point. So that's an interesting application, combining quantum with a correlation engine and building all of that into one solution. We heard about quantum neural networks, but of course we also care about the regular neural networks that we have today. And there the question is, could we train neural networks, regular current neural networks, by using a quadratic optimizer? It turns out that is possible. There are a few steps that one needs to take. There is kind of a regression part, the quadratic optimization running on the special hardware that we have, and then you kind of get the trained model out. Of course, this is a simplification because we don't really have a lot of time here, but just to show what it is that we're working on right now on the research front of where things are going. So given that it's a little bit late already, I'm just going to quickly get through, because we're here in Abu Dhabi, we have an energy example as well. we're working together with a company called Qubit Engineering to optimize wind farms, again, translating the problem into QUBOs. Two problems that we can translate here. One is where to put the wind farm, the actual rotors, which way to face them, where to put the towers. The second one is, as it's operating, need to predict the energy consumption, as well as wind that is going and the direction of the wind. And so you optimize the operation. In general, what people want to know is when to turn it on, when to turn it off, when it's going to be profitable to run the wind farm and when it isn't. So there's some nice QUBO solutions for this, and in this collaboration, as I said, with Qubit Engineering. So this is a little view of how this looks like, and thank you very much. Forward to some questions.
For the Groq optimizer, that's all going to depend on the algorithm you use to update the weights in there. I mean, when I maybe didn't catch it right, it looked like there was a gradient descent kind of algorithm, but there are other ways to do that. Can you comment on it?
Yes. So the way we operate is we have a core engine that allows us to do the core inner computation very quickly. And then the way I think of this is projects with particular other parties. So everybody who wants to do a particular thing will need a completely different solution. So we are not trying to build our own complete solution. We just have the core, and then we have a project to develop something for a particular use case.
You're basically saying that that's programmable so that each project can kind of figure out the optimization that works best for them.
Programmable, as well as developed in a collaborative fashion, where we would start a project together with another party that wants to develop that and develop the science and the implementation.
Okay, thank you.
Hi. It's kind of a follow-up on what John just said in some sense. So you mentioned, I think I saw your slide, simulated bifurcation, which I suppose is the algorithm of Goto. I don't know, the Japanese, like using the Toshiba machines, I guess.
Simulated bifurcation is really just the physics behind how the quantum computer works that we are simulating with our QUBO implementation.
Oh, okay.
So we stop at the QUBO.
Okay, so that's not that algorithm that you are...
No, we just compute the quadratic unconstrained binary optimization, which is this matrix thing.
Okay, so you do not have any way to solve it at the moment. You cannot show like a performance in terms of time to solution, for example, something like that.
We do for QUBO matrices.
Yeah, so you didn't show that, right?
I didn't show that because then I would have to spend a lot more time on how we measure that, how we derive the numbers.
But did you compare against, I don't know, Fujitsu, NTT, Toshiba?
So Fujitsu, yes. So, well, Fujitsu is not necessary because Fujitsu has stopped making their chip and they're not selling it anymore because it's slower than the GPUs. So it's sufficient to just compare to the GPUs. And we have some different comparisons, depends on A100, H100. You want to compare on energy, you want to compare on... So there's a whole talk that I could give where we are faster than the GPUs. But depending on the problem size and depending on some the driver issues, we sometimes are better suited and sometimes less. Yeah. I think there was the way in the back.
Yeah, thank you for the interesting talk. It's the first that I saw implementation of a data flow engine. What I want to ask, if I understood correctly, you have something like 130 gigabytes of SRAM in the machines. Because if you have 225K variables, I mean, full quadratic matrix, FP16, that would mean you have, yeah, about 130 gigabytes.
So each chip has 200 megabytes.
Yes.
And you can put together up to 20 racks, which is 1,200 chips.
So
a lot, yes.
Yeah, but we are talking about 225K full dense matrix for the QUBO.
Yes.
In FP16 only.
Yes.
Okay, yeah, because then actually what I really would also like the previous speaker, to see some quality, results on the quality, because what I really wonder is, I mean, you can connect this and you can distribute this, but it's a global optimization problem in a sense. So the chips have to communicate and change stuff. I mean, if you're doing kind of, bifurcation or whatever, it's a heuristic solution, so it depends very much on how good the result in the very end is.
Absolutely.
Yeah.
So that's why I'm using the integer factorization as the benchmark, because in integer factorization there is no good enough. Either you found it or you didn't find it. So either you factored it or you didn't factor it. There is no how good it is. And so we use that in order to test the implementation. And that's why I said there is a problem with showing all the performance numbers. It would take a long time. But I'm very happy to do that later on and follow up.
Is there a paper about it?
Well, not yet. We are still in the actual commercial work with clients. We're keeping it confidential, but I hope that we'll be able to publish something in the next few years. There is just a paper just came out about what we did 6-7 years ago. So the publications are lagging a little bit the reality.
Thank you very much.
Hi, thank you for the talk. So you mentioned factorization, and the mapping you use is this QUBO mapping, right? And there are reasons to believe, I guess Michele Mosca made some argument about it, that mapping integer factorization to a binary encoding is could lead to actually a more complicated problem than what factorization actually is. So my point was, given that you have a great hardware, just for the case of factorization, wouldn't be perhaps a better route to implement a very efficient algorithm for factorization rather than QUBO? I mean, I'm sorry, I'm phrasing it this way, but that example caught my attention.
You are 100% right. There are elliptic curves methods that would be a lot more efficient for solving the factorization problem. We're not trying to solve the factorization problem. We're trying to get rid of the problem of how good is the result by using a problem where there is no goodness of the result, but there is an actual factor. You found the factor and it is the one that you need to test the quality, the speed, and the implementation that we have. So we know that we get the right result. It's not about how close are you to the optimum, but we find the actual factor. And we use the factorization to challenge ourselves to get the implementation of the QUBO right. If we wanted to solve factorization, yes, the elliptic curves better. Yes, absolutely.